All right, so here for 1.7, looking at periodic table trends, it says what happens to the number of protons in the nucleus as I move from left to right across the periodic table. So if we take a look at our periodic table, we can see as I move from left to right, we know the number of protons are getting bigger, right? So lithium, beryllium, boron, carbon. So if I'm going from left to right, we're obviously getting more protons in the nucleus. So your number of protons would increase. All right, so here we can for sure tell the number of protons does increase going from left to right. Right, so the number of protons is going to increase. So it says electrons removed from an atom, would it take more or less energy? So every time we're thinking about periodic table trends, what we really want to look at or think about is what's happening to Coulomb's law. So what is going on in Coulomb's law is what we're really referring to. So if it is closer to the nucleus, is it going to take more energy in order to remove it away? So in that case, once again, think in terms of Coulomb's law. Is it going to be harder to remove that nucleus? So it's kind of like when I was talking about. All right, so anytime we're thinking about these kind of things in terms of periodic table trends and different forces, always think in terms of Coulomb's law. So if I get something that's going to be closer to the nucleus, what is really happening? Well, we know that radius is going to get smaller. So if that gets smaller, then the force gets greater. So if the force gets greater, remember this is the force of attraction. So therefore, it's going to be much harder to remove this electron because it's being highly attracted to the nucleus. So therefore, here, if it's closer to the nucleus, smaller radius. So we have a much smaller radius, which means that we're going to have a higher attraction and a higher force. Therefore, it's going to be harder to remove that electron. Same scenario, exactly the opposite. If it's further from the nucleus, we're going to get a larger radius, and therefore we're going to have a smaller force and a smaller, so therefore a smaller attraction and easier to remove. All right, so here, using the concept of effective nuclear charge, explain why the size of the atom generally decreases. So effective nuclear charge is, once again, how easy it is for something to hold on to that electron. So if I'm going across going from left to right, so let's just look at our periodic table here for a second. So if I'm going across from left to right, here we're adding more protons to the nucleus. So if I think about it, adding a more magnet to the nucleus. So we're putting everything, so it's the same shells. So in other words, everything is like got two, so in that second period, everything has two rings, right? So the first one, there's one electron, and outside, second one, there's two electrons. But what did we do? We increased it. There's one proton here, there's another proton, so it's like plus two. I should say plus, but there's three protons, four protons, five protons in the nucleus. So, but they're the same ring, so that is being drawn in much tighter. So as we add more protons, we call that a greater effective nuclear charge because we've added more protons to the nucleus. So when we add more protons to the nucleus, but have the same shell or same number of rings, we have a greater effective nuclear charge, which means the nucleus is better at drawing those electrons into the center, which means our ring gets smaller and the radius gets smaller. Okay? Here, why is a cation smaller than its atom and an anion is larger? So first off, let's just remind ourselves, what is a cation? A cation is anything with a positive charge. So that would be like example of magnesium plus 2. An anion is something with a negative charge, or like fluorine with a -1. So let's look at magnesium regular, which has, let's say, 3 rings. And magnesium plus 2, what did we do? We removed that outer ring. So a cation is smaller than its neutral because we have removed a shell, or in other words, we've reduced the so we've reduced the shielding, and so we remove that shell, making the radius smaller, and so that's what makes it smaller, because we've reduced the shielding, so the electrons in the center don't shield the nucleus as much because we don't have as many rings, so therefore we reduce the shielding, making that smaller. So here, now we're adding an electron. So when you add an electron, what do you technically do? You increase the electron pair repulsions. And so when you increase the electron pair repulsion, we're going to make these electrons spread out. So that's what makes the anion bigger, is due to this increase in electron pair repulsions. All right, so now we're talking about how can Coulomb's law help explain ionization energy. Well, first let's discuss what is ionization energy. We know that's simply the energy to remove an electron. So we have an atom with an electron out here, and we're wanting to take it away. So we know that electron is being attracted to the nucleus. So there's some attraction to the nucleus, which is what holds it in place. So the further the electron is away, the less attraction. So we know, if I'm once again talking about Coulomb's law, charge over radius squared. So if the distance is further, the force is smaller. So that's that force of attraction is smaller, and therefore it's easier to remove. So this would have a low ionization energy, because ionization energy is essentially the force. So if the force gets smaller, the ionization energy gets smaller. If our distance is closer, or in other words, radius is smaller, then our force of attraction gets greater. Right? So our force gets greater, which means our ionization energy is getting greater. All right, so here for 15A, if you remove an electron from an identical neutral atom. So is it going to, if I take an atom and I say an identical neutral atom, so chlorine versus chlorine, obviously this is going to be the same, because why? We have the same protons, so same number of protons. So therefore, we have the same number of electrons, so same shielding, same number of rings, same effective nuclear charge. So you're going to hear that term a lot, effective nuclear charge. We use that to explain a lot in this section, and it comes up. So Coulomb's law is a very important concept in a lot of AP chemistry, and we use it to explain a lot of different things. All right, so if we're talking about a cation, so let's go back to our magnesium plus 2. So if we have a cation, we know we've removed this outside shell as compared to its neutral. So if I'm going to compare magnesium, which is its neutral, compared to the cation would have a much higher ionization energy. So Mg plus 2 would have a much higher ionization energy. than Mg because Mg plus 2 is a smaller radius. So according to Coulomb's law, it's got it right. So since it's a smaller radius, it has a higher force. So it has a higher attraction and therefore a higher ionization energy due to that decrease in the radius because we removed that shell and decreased the shielding. All right, same reverse concept. If we're talking about an anion, we know we have an increase in the electron pair repulsions. So an increase in electron pair repulsions makes it larger. So we have a larger radius. And when we have a larger radius, we know then our force is going to be smaller. So therefore, our ionization energy is smaller. So because it's going to be easier to remove when it's got a larger radius. Same way, electron removed from a different atom, but a larger atom. So once again, if the radius is larger, so if the radius increases, so once again, looking at Coulomb's law, if radius goes up, we know force must go down. So therefore, we're going to have a smaller ionization energy. Now here, if we're in the same period, so meaning we're going across left to right, so we add more protons. So what happens when we add more protons? We get a greater effective nuclear charge. And instead of writing effective nuclear charge, a lot of times we just, because protons, we can abbreviate them with Z. So we'll say it's greater Z effective, which means greater effective nuclear charge. So greater effective nuclear charge or greater Z effective means that it's being held more tightly. So therefore, we're going to get an increase in the ionization energy as I move from left to right, going across. So if I'm going from left to right across the periodic table, we're going to get an increase in the ionization energy due to this greater Z effective. Same group with fewer protons, it's absolutely the reverse. We have a decrease in the effective nuclear charge or decrease in Z effective, which means the ionization energy is going to be less. All right, for 16A, explain why the ionization energy jumps when removing the fourth. So why do we have this giant jump between the third and the fourth? Well, that means that we must be significantly further away. So we have a large jump in the radius, which would make that deep. So we have it's like electron 1, electron 2, electron 3. So that would be like something that has 3 valence electrons. So if this is 3 valence electrons, this must be in a new shell. Right, so some new shell much further away from the nucleus. So how can we use this to determine the number of valence electrons? Well, when we see this big jump, this must be a new shell. Therefore, all 3 of these are in an internal shell. So we know this is something that is in the third group or third column or something that has a +3 charge or 3 valence electrons. All right, so it says element X has an electron configuration of that. So we know that's essentially sodium. This 1s2, 2s2, 2p5. I know that is fluorine. So we're really comparing sodium and fluorine. So let's look at our periodic table and say, okay, well, we're comparing sodium and fluorine. So sodium as compared to fluorine, so group 3 up here. So we've gone down a group, we've increased the radius. So which one would have a greater ionization energy? Well, here we have another ring. So this would have a lower ionization energy. Fluorine would have a much higher ionization energy. Which element would have a larger radius? Well, obviously this has 3 rings as compared to fluorine having 2. So sodium would have a much larger radius. which element would have the higher electronegativity? Well, electronegativity is how easy something is to attract electrons. So the smaller it is, so the smaller atoms have a higher electronegativity. So what we really want to look at here when we're thinking about electronegativity is we want something, so the high electronegativity have a very, very high Z effective. So a lot of protons in their nucleus, and as low a radius as possible. So we want this combination gives us the highest electronegativity. So something that attracts electrons very easily because it has a very high Z effective, a low radius, and so because it's a low radius, it has low shielding. All right, which element would form an ion that has a larger radius? So if we're comparing Na as compared to fluorine, if this makes an ion, it's going to be Na plus. If this makes an ion, it's going to be F minus 1. Well, we know anions get bigger, so anions get bigger, cations get smaller, and these would both be associated, even though, so they would both be associated with making that into neon, but it's neon with 11 protons as compared to neon with 9 protons when we're looking at them. So even though they're electrically the same element, they do not have the same protons. So 9 protons in the nucleus, 11 protons in the nucleus. Sodium would be smaller because it has a greater Z effective. There we go. So there's sodium with a greater Z effective. Which element would release more energy when it gains an electron? So gaining an electron is really looking at what we call electron affinity. So how easy does it gain an electron? Well, we know that fluorine wants to gain electrons and sodium has absolutely no use for electrons. It actually wants to get rid of them, right, to make that +1. So we know that fluorine would gain a lot more energy. So would gain a lot more energy by when it gains that extra electron. All right, so here element X, we know 2p3, so therefore we know that means that it has 5 valence electrons. We know 2s2, 2p5, that means it has 7 valence electrons. And 2s2, 2p, that means 3s1, that means it has 1 valence electron. So their element X, if it has 5 valence electrons, we know it wants to get 8, so therefore it needs to gain an additional 3. So this would typically give you a -3 charge. Something in this, like fluorine, 7 valence electrons, is going to want 1 more and be -1. And element Z with 3s1 is going to likely get rid of this extra 1 to give me back to 8, and that's why this would be +1. What compound would X form if it bonded with magnesium? So let's first think, what is X? So 2s2. So element X we know is nitrogen. So if I was to form that with a magnesium, so magnesium +2 and a nitrogen -3, we know how to put those together, and that would give us Mg3N2, right? And so forth and so on for the rest of those. And we know part C, it would be anything in the same group, right? So anything in the same group, or in other words, the same column, because they have the same chemical properties and the same number of valence electrons. So any of these elements would be identical if they bonded with X, as long as they're in the same group, the same column.